looking at the calculating the area under the curve for the velocity v equal t squared on the interval from 0 to 2, we kind of concluded just by looking at two examples that the more rectangles you can squeeze in, the better your approximation. And this is a website that has a Java applet that really illustrates that well. We were using the right endpoint. First of all, there's a little issue with how the function showed up in this. This should be y equals x squared. And in this, for here, we're just looking at it from 0 to 1, but we're still going to get the same idea. We were using the right endpoint, so I'm going to choose RRAM. More on that in a minute. And what we see right there is two rectangles used to approximate the area under y equal x squared from 0 to 1. You can see the rectangles stick up above the curve a significant amount, so this is not a very good approximation. But if I click to increase the number of rectangles, now I've got 4 rectangles, and we can see that those 4 rectangles, if we summed those 4 areas, we'd have a closer approximation of the area under the curve. If I increase that again, okay, definitely we got 8 rectangles, definitely fits better. Again, 16 rectangles, we are getting closer. 32 rectangles, even closer. This is actually very, very good at this point. There's 64 rectangles, so you can see that as you increase the number of rectangles, the area of the rectangles becomes a lot closer to the actual area under the curve. And now all the little lines have run together, so it's very, very close. Now the other thing that I kind of like about this website is that it makes it easy for you to take a look at rectangular approximation, not just using the right endpoint. We could choose to use the left endpoint, which would be LRAM. Same thing. Now we're using the left endpoint of each interval. If we've divided it into 2 intervals, the first endpoint that we're plugging in to y equal x squared to get a height is 0. 0 squared is 0. So we've got a rectangle right there with no area, and then the second rectangle uses the endpoint 1/2 to get height. If you increase the number of rectangles, what you see here is that our rectangles are not very close to approximating area under the curve. But as you allow the number of rectangles to increase, we'll see that these rectangle areas are getting a lot closer to being the actual area under the curve. Well, we can use the right endpoint of each interval, we can use the left endpoint of each interval, or we could use a midpoint of each interval. There's using the midpoint to calculate the height of the rectangle. You can see that if you imagine where 1/4 is, which would be the midpoint of the interval from 0 to 1/2, 1/4 squared would give us this height right there. So we'd have an area of a rectangle that would be length times width there. Here's another rectangle, and just at first glance, at least with this example, the midpoint rectangles seem to come a lot closer to actually approximating area under the curve. Again, allowing the number of rectangles to increase, you can see that the more rectangles you squeeze in there, the much better your approximation is going to be. Now if I stop right there with 16 rectangles, you can almost imagine taking the little piece of the rectangle that sticks up above the curve and sort of flipping it over and plugging it in to sort of fill the gap. I can use my pointer right here. If you took this little piece of the rectangle right there and flipped it around, it almost would fill the gap right there. So we're getting very, very good approximations. And the point of this exercise, and you can get on this website and play around with it, but the point of this exercise is to realize that to calculate the actual exact area under a curve, which in the context of the problem that we're looking at would give us the exact displacement of the object that's moving, we'd have to be able to squeeze in an infinite number of rectangles. I have a calculator program that's going to do rectangular approximation for us. So I'm going to pull up my calculator. Now for this program to work, first of all you have to have a TI-83 or a TI-84. Those of you working with TI-89s, this program will not work. You can just kind of view this demonstration, that'll be fine. You have to enter the function in Y1. Your equation that you're trying to calculate the area under the curve for has to be in y1. If it's someplace else, this won't work. So I've entered y equal x squared. And if I go back to the home screen, quit and go home, I'm going to press program, and this is the RAM program that I'm going to be running. So I'm going to select RAM and press enter to tell the calculator that yes, that's what you'd like it to do. Now the calculator is going to ask you for some input. We need to tell it what interval. Well, in the example we were working in the previous video, I was looking at the interval on y equal x squared from 0. So I'll tell it the endpoint A is 0 to 2. Okay, tell it the endpoint B is 2. And we were working with 4 subintervals. Okay, so I'm going to go with y equal with 4 subintervals again, and I press enter. Calculator's going to think for a bit, and then what this does, this program gives you all 3 rectangular approximations. If we use the left endpoint, we'd have an approximate area 1.75. If we'd use the midpoint of the 4 intervals to calculate the height of the rectangles, we'd have 2.625 for the area, and then the right endpoint, which is what we did, you get 3.75. And what you can do with this program is you can run it a number of times with larger and larger numbers of subintervals. So that was 4. If we go with 8 subintervals, we get those 3 numbers. If we run it again, and I'm just going to go kind of ahead and jump in with sort of a big number for the number of subintervals, maybe 64. Okay, calculator's going to have to think for a good, it's going to have to work a little bit. Chug, 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 work, work, work. Now, what I want you to notice about the left sum, the midpoint sum, and the right sum, or these approximations, is that the larger the number of subintervals you have, the closer those 3 numbers are to being the same. Okay, and they're all 3 getting closer to being the same because they're all 3 getting closer to being the exact area under the curve. So we could kind of conclude that to find an exact area under a curve, you'd have to think about taking a limit as the number of subintervals approaches infinity. The more subintervals, the bigger that number, the more rectangles you've got squeezed in, the less wasted space you have. So this is where the idea of a limit is going to come in to be important for us when we're working with areas.